Now for the complex eigenvalue. So let lambda 1 be equal to alpha plus I times beta. Right. Again, alpha is the real part and beta is the imaginary part. So be a complex eigenvalue of the coefficient matrix. Capital A in the homogeneous system. X prime equal to A times X. And let U and V denote the column vector. There you have the solution. Solution 1 is U times cosine of beta t minus V times sine of beta t times e to the lambda alpha t. Sorry. And x2 equal to V times cosine of beta t plus U times sine of beta t times e to the alpha t are linearly independent solutions of the homogeneous system. So the theorem for the complex eigenvalue is that you deal with the complex number. And for the complex number, there's always real part and imaginary part. When you solve the system, right, you have to solve the characteristic equations in terms of the determinant of A minus lambda I equals 0, and you're going to get some complex number. And for complex number, that is the eigenvalues. When you have the eigenvalues, you can solve for the eigenvectors, and the eigenvectors eventually it's going to get into the form of a complex number. You will see in a minute. From that complex number for the eigenvector, you can deduce the value of vector u and of vector v. Right, so you have to be careful. This is a little bit different from when you solve for the second order differential equation when you have the complex root. Right? Because not only you have the complex eigenvalues, but also the complex eigenvector. So let's get started here. So you have the system x prime equal to 2, 8, negative 1, negative 2, multiply with x. Right, so that's the homogeneous system. And you are also given the initial conditions of x of 0 equal to 2, negative 1. Okay, you have the coefficients. You're going to find the eigenvalues using the characteristic equations. So use the characteristic equations. The determinant of A minus lambda I equal to 0 to solve for eigenvalues. Right, so we get that A minus lambda I equal to the determinant of 2 minus lambda. This is 8, this is negative 1, this is negative 2 minus lambda equal to 0. And again, this is a 2 by 2 determinant. You can solve this assembly easily. So you get 2 minus lambda times negative 2 minus lambda minus negative 1 times positive 8 equal to 0. Right, so now you expand the equations, combine like terms, and try to find the value of lambda. So you have negative 4 minus 2 lambda plus 2 lambda plus lambda square plus 8 equal to 0. So this two term cancel out. And you left with lambda square plus 4 equal to 0. And here you get lambda square equal to 4 or lambda equal to, sorry, negative 4. Instead of negative 4, you can do this as 4 times I squared. Right, 4I squared is equal to negative 1. When you take the square root on both sides of the equation, you obtain plus minus 2i. Right, so obviously you have a complex number. And because this calculation gives you two eigenvalues, one is 2i, the other one is negative 2i. So you can actually find the corresponding eigenvector. Here, we obtain two eigenvalues. Lambda 1 equal to positive 2i, and lambda 2 is equal to negative 2i. All right, so when lambda 1 equal to 2i, now you go back to the theorem again. So in this case, the eigenvalue is of the form alpha plus I beta. For alpha is the real part and beta is the imaginary part. Okay. So in this case, you have that alpha is equal to 0 and beta is equal to 2. Right, so let me take a quick note here. Alpha is the real part and beta is the imaginary part. So you get the real part and you get the imaginary part. Now you have the eigenvalues. You substitute into the equations a minus lambda I times v equal to vector 0 to solve for the eigenvector. Okay, so substitute lambda 1 into the equations a minus lambda I. So instead of vector v, let me slightly use a different notations. I'm going to use vector w to find the representation of the eigenvector or the corresponding eigenvector w. So that is, so for a minus lambda I, you get the form already. So it's very similar to, for the entry, very similar to the entry inside this determinant. So lambda is equal to 2 positive 2i, so you get 2 minus 2i, 8, negative 1, and negative 2 minus positive 2i. So you get 2 minus 2i, 8, negative 1, negative 2 minus 2i, times w1, w2 equal to 0, 0. From this matrix vector equations, you're going to rewrite that as a system of linear equations. So you get 2 minus 2i times w1 plus a times w2 equal to 0, and negative w1 plus negative 2 minus 2i w2 equal to 0. So from these two equations, you choose one equations to work with, right? So I'm going to choose, because they are, believe it or not, they are equivalent to one another, okay? Just similar to the last two cases that we have done, okay? So therefore, you just use one of the equations to work with. If you, let's say for this example, we're going to use the second equation because it's a lot nicer. It's easy to solve for W1 in terms of W2, right? But if you want, you can work out the same details and you're going to have the same eigenvectors at the end. All right, so from here, I'm going to get that negative W1 plus negative 2 minus 2i W2 equal to 0, or W1 is equal to negative 2 minus 2i times W2. So in this case, W2 is the free variable, right? And as you notice that inside the parentheses that you have negative sign. So we're going to take negative sign as the common factor in this case. And now to avoid negative number or fractions, if you encounter something related to fractions, then you choose the free variable in a way that make your problem easier to deal with, right? As long as it's not going to be a trivial solution. That means you don't want it back to 0. All right, so in this case, we choose W2 to be equal to negative 1. Then you have that W1 is equal to 2 plus 2i. So the eigenvector has two entries because we are dealing with a 2 by 2 matrix, right? The first entry is 2 plus 2i, and the second entry is negative 1. Then, first, the eigenvector is the W equal to W1, W2. Now W1 is equal to 2 plus 2i, and W2 is negative 1. So from here, what you do is now you have an eigenvector already, but it's still in the form of complex number. Right? Look at the first entry, you can see that's 2 plus 2i. So you want to separate this vector into vectors that contain real part only and a vector that contain the imaginary part only. So here, I'm going to do 2, negative 1, because this 2 right here is the real part. And negative 1 doesn't have I attached on that. So that is the real part as well. Plus 2 times I, like that, right? So the first entry is 2. That is the imaginary part. This 2 is the imaginary part. Okay. And for the second entry, like there's no imaginary part. So that means the entry is equal to 0. So that is 0. So this one is U. And this one is V. Then the solutions of this eigenvalue, lambda 1 equal to 2i, is x1 equal to, now you go to the theorem up here, and you see that we show the solution without proof, right? That u times cosine of beta t minus v times sine of beta t times e to the lambda t. Remember a few things here, right? As you work through the problem, you remember that lambda in our case is equal to 0, right? So the exponential term is not there, right? Because e to the 0 is 1. Beta is equal to 2, right? So eventually you're going to have cosine of 2t and sine of 2t. U is the real part that you see that we just obtained, and V is the imaginary part of the eigenvector that we just obtained. So the solution is going to be equal to 2 negative 1 times cosine of 2t. Let me be careful here. Let me take one more step, sorry about this, to rewrite the formula minus V times sine of 2t times e to the alpha t, right, where alpha is equal to 0, beta is equal to 2, u is equal to 2 negative 1, and v is equal to 0. Right? Then you have that x1 is equal to 2 negative 1 times cosine of 2t minus v, which is 2, 0, times sine of 2t times e to the 0. This is too much detail. I just want to show you where all the numbers coming from, but if you know where the numbers coming from, you can skip all the steps and just give me the answer. So x1 in this case going to be 2 negative 1 cosine of 2t minus 2, 0 sine of 2t. Right. Again, e to the 0 is equal to 1. Now, lucky for us, we don't have to go through the proof to get the second solution. The second solution is in fact given to us as well, and is in the form of v times cosine of beta plus u times sine of beta, and u and v are the v is the imaginary part of the eigenvectors, and u is the real part of the eigenvector. And you may ask the questions, what happened to the second eigenvalue? Right, you have a second eigenvalue, which is equal to negative 2i. It turns out that when you work out the details, you have the same imaginary part of the eigenvalue and the real part of the eigenvalue. Hence, they just off the negative sign. Hence, the second solutions. And it looks very similar to the first solution. But that's good for us, right? If you just pick out, if you have two eigenvalues, just pick one eigenvalue to work with, and the second solution will follow using this formula. And the second solution is equal to 2, 0 times cosine of 2t plus 2 negative 1 times sine of 2t. So you have two solutions. You can write down general solutions to the homogeneous system. Again, you're allowed to do that because x1 and x2 are linearly independent. The general solutions of the homogeneous system is, so you have x equal to c1 x1 plus c2 x2. In this case, you have c1 equal to 2 negative 1 times cosine of 2t minus 2, 0 times sine of 2t plus c2 times 2, 0 times cosine of 2t plus 2 negative 1 times sine of 2t. Now, if you want to make the solution look nicer, you can just combine the two, these two vectors together, right? These two vectors together, these two vectors together. Right? So C1 times 2 cosine of 2t minus 2 times sine of 2t. So that's the first entry. And the second entry is just negative cosine of 2t. So that's the vector going along with C1. And plus C2 times 2 cosine of 2t plus 2 sine of 2t. And the second entry is negative sine of 2t. And that is the general solutions of the homogeneous system. And this homogeneous system gives us the complex eigenvalues and complex eigenvector. All right, so furthermore, you are given the initial conditions, and the initial condition is x of 0 equal to 2, negative 1. So given the initial conditions, x of 0 equal to 2, negative 1, we can solve for C1 and C2. That is, so that means in this case, t is equal to 0. So here you let t equal to 0, you substitute into the general solutions. You get x of 0 equal to C1 times 2 cosine of 0 minus 2 times sine of 0 minus cosine of 0 plus C2 times 2 cosine of 0 plus 2 times sine of 0. And this is sine of 0. So sine of 0 is equal to 0. And cosine of 0 is equal to 1. So you rewrite your vectors as 2, negative 1, plus C2 times 2, 0. And this is equal to 2, negative 1. And from here, of course, you can get the system of linear equations that help you to solve the C1 and the C2. So you get 2C1 plus 2C2 equal to 2, and negative C1 plus 0C2 equal to negative 1. From the second equation, you can automatically get that C1 is equal to positive 1. And here you get that C1 is equal to positive 1. So C2 is equal to 0. Thus, the particular solutions is, so x equal to, so C2 is equal to 0. So this part of the solution doesn't matter to vanish. Right? C1 equal to 1. So you're left with just 2 cosine of 2t minus 2 times sine of 2t. And this is negative cosine of 2t. So I'm going to give you another example on the complex eigenvalues. But we're not going to spend time on the initial value problem. We're just going to obtain the eigenvalues and the corresponding eigenvector, and we're going to write down general solutions from the findings. Okay. So the next example, find the solutions of the system. You have dx dt equal to 6x minus y, and dy dt equal to 5x plus 4y. So from the system, you can rewrite it in terms of the matrix vector form. Right? So here you get x prime equal to the matrix 6, negative 1, 5, 4 times x. So we get the coefficient matrix. This allows us to find the eigenvalues. Right. So the eigenvalue can be determined using the characteristic equations as, so you have the determinant of 6 minus lambda, negative 1, 5, 4 minus lambda equal to 0. Again, this is a 2 by 2 determinant. You get 6 minus lambda times 4 minus lambda minus 5 times negative 1 equal to 0. here you get, so 6 times 4 is 24 minus 6 lambda minus 4 lambda plus lambda square plus 5 equals 0. Here you get lambda square minus 10 lambda plus 29 equals 0. So obviously it's not trivial to factor this quadratic equation, so you need to find the solution using quadratic formula. Okay, so using the quadratic formula, we get that lambda equal to 10 plus and minus square root of 10 squared minus 4 times 29 altogether divided by 2. So this one is square root of negative 16 divided by 2. So 10 plus and minus 16i squared divided by 2. So you have 10 plus and minus 4i divided by 2. You get 5 plus and minus 2i. So that's the answer. You get two eigenvalues. One is 5 plus 2i and the other one is 5 plus 5 minus 2i. Obviously, this is a complex number. So you can see you have a real part and imaginary part. So alpha is equal to 5 and beta is equal to 2. So here you get alpha equal to 5 and beta is equal to 2. The eigenvalues are lambda 1 equal to 5 plus 2i and lambda 2 equal to 5 minus 2i. Again, you're just going to take one eigenvalue to work with. That is when lambda 1 equal to 5 plus 2i, we can determine the corresponding eigenvector using the formula a minus lambda I times w equal to 0. So here, for a minus lambda I, it's going to be the same with the entries that we have here in this determinant. So 6 minus lambda, in this case 5 plus 2i, minus 1, and then 5, and 4 minus 5 plus 2i. So you get 6 minus 5 plus 2i, negative 1, 5, and this is 4 minus 5 plus 2i, times w1, w2 equal to 0, 0. Right. So from here, you can rewrite this matrix vector form as a system of linear equations. Or you can simplify the entries a little bit here. So you get 1 minus 2i minus 1, this is 5. This is negative 1 minus 2i. w1, w2, 0, 0. Then you get 1 minus 2i times w1 minus w2 equal to 0. And 5w1 minus 1 plus 2i times w2 equal to 0. If you notice, it's easy to solve for w2 in terms of w1 in the first equations. So here we get w2 is equal to 1 minus 2i times w1. And w1 in this case is a free variable. So here we choose w1 to be equal to 1. Again, because it's a free variable, you can choose anything you like, any number you like for w1, as long as you don't have a trivial solutions or a zero vector. So we choose w1 to be equal to 1. Then w2 is equal to 1 minus 2i. Thus, the eigenvector is so w equal to w1, w2. Well, this is equal to 1 minus 2i. Again, you are still dealing with the complex number. Right? So you want to separate this eigenvector into the real part and the imaginary part, like a column of real part and a column vector of imaginary part. So you have 1, 1 plus 0, negative 2i. So again, this is real part. This one is real part plus 1, 1. There's no imaginary part in the first entry, so that is 0. And -2 is the imaginary part in the second. So that's what you get. This is u, and this is v. The solutions are, remember again, this is not going to prove where the second solution's coming from, right? But using the formula that we get earlier up here, you can just write down the solution x1 and the solution x2 based on the information that we got. We got the real part of the eigenvector, we get the imaginary part of the eigenvector. You get alpha, which is the real part of eigenvalues, and beta, which is the imaginary part of eigenvalue. So x1 is equal to 1, 1 times cosine of 2t minus 0, -2 sine of 2t times e to the 5t. So alpha is equal to 2, alpha is equal to 5 and beta is equal to 2. That's what you get the results. x2 is equal to 0, -2 times cosine of 2t plus 1, 1 times sine of 2t times e to the 5t. All right, so that's it for me for the complex number.